All right, here are some solutions to the remaining few screens of our very last Desmos activity with statistics. So this was screen 8, mentioning mean, median, and mode. We're headed towards standard deviation. We've already seen range. Just as a quick reminder while we're right here, this fancy notation X bar means to find the mean, so you may see that in other contexts. We have information from San Diego about all of the temperatures for 7 days. We need to find the standard deviation, and that means first we need to find the mean. I did that already. The mean is 75 degrees. And then for each deviation, first we have to go through and find those. So you'll take the individual temperatures and subtract the mean. So 72 minus 75 would give us -3. 73 minus the mean of 75 would give us -2, and so on. You'll find all of those deviations for this middle column. And when you add those up, those are always supposed to give you 0. Make sure you get a 0 right there before moving on. Once you have the deviations, then we find the squares of those deviations. So we take the item times itself, or the deviation times itself. And so I gave you a couple of them outlined here. We should get 9 for a square, and then 4, and then 1. A couple of zeros, 4 and 16, and then we add those all together. So find the total, and that should be 34 in this case. So what we've done in this table is we've found each temperature's distance from the mean, and then we took those distances and squared them. And now we have a total of those deviations or distances. And then we need 2 more steps to find the standard deviation, and I tell you what they are in the written portion. You're supposed to take the sum of the squares, divide by 1 fewer than the number of data points that we have. So we had 7 days worth of temperatures, so in this case we'll divide by 6. If you do 34 divided by 6, you get a long decimal number. That's called the variance. You would need to take the square root of that to get the standard deviation, and when we round that to the nearest hundredth, we'll get 2.38 degrees. The unit for standard deviation matches the unit that we started with. We started in degrees, and we will end in degrees. So 2.38 is a measure of approximately the average distance each data point is from the mean. We're going to use this value and compare to another data set of temperatures to kind of get a better feel for what it does. So then we have Long Beach temperatures listed. We need to do exactly the same thing. The mean here is also 75. You should double check me on that, but it's meant to be the same thing. So we go through and find all of the deviations, all of the little gaps from the mean. When we add them together, we should get 0. When we square all of those deviations and add all of those together, I think we get 58. So this time when we find the standard deviation, we'll do 58 divided by 6, and then take the square root, and we'll get 3.11 degrees rounded to the nearest hundredth. So Long Beach has a greater standard deviation than San Diego did for the temperatures, and that means the temperatures in Long Beach were less consistent. They jumped around more than they did in San Diego. So here San Diego had a standard deviation of 2.38 degrees. Long Beach had a standard deviation of 3.11 degrees for that week's worth of data that we had for each city. And the smaller standard deviation tells us that that has the more consistent temperatures because they don't jump around as much. So San Diego ended up being more consistent. We do a little bit of work this semester with normally distributed data, or things that are approximately normally distributed. So we need to know this rule about 68, 95, and 99.7%. So I leave you with this to read. And then we need to go use it. So I give you that we have a collection of low-calorie snack foods following an approximately normal distribution for the number of calories in them. So somebody's already done the work behind the scenes. We know that the mean is 100 calories and the standard deviation is 15 calories. To make the graph with all of its labels, you'll put the mean in first. So the mean is 100. And then as you move up standard deviations, you will add 15 calories. So we start at 100 for the mean, add 15 calories to get to 115, add 15 more calories to get to 130, add 15 more calories to get to 145. So that's 1, 2, and 3 standard deviations above the mean. Those are their calorie counts. To go below the mean, we subtract instead of add. 100 minus 15 would be 85. 85 minus 15 more would be 70. 70 minus 15 would be 55. So that's 1, 2, and 3 standard deviations below the mean, and everything on here would be labeled as calories. Question for us. We want to talk about the percentage of snack foods between 85 calories and 115 calories, and I noted them with the green arrows here. Here's 85 and 115. 85 is one standard deviation below the mean, and 115 is one standard deviation above the mean, and that means that we are within one standard deviation. That's that wording within, one above and one below. And that means from the empirical rule that we would expect 68% of our snack foods to have those calorie contents. If we go back one screen, it was from one below to one above captures 68% of whatever we're talking about in terms of data points. So that should be 68%. Oh, I have a follow-up question I didn't do yet. Between 70 and 130. Let's find those. 70 calories is, I didn't want that. Yeah. 70 calories is right there, and 130 calories is right there. So in this case, we're going from 2 standard deviations below to 2 standard deviations above. That's within 2 standard deviations. So as a percentage within 2 standard deviations, if you didn't write it down, you come back and grab it, and that's 95%. (95% of the snack foods will be in that range between 70 and 130. And then if we had 400 different snack foods that had been surveyed, we would expect how many of them to have calorie contents between 55 and 145. And I note that I want a number of snack foods, not a percentage. First, let's grab 55 to 145 and see where those are on the plot. 55 is right there. 145 is right there. So this question involves being 3 standard deviations below the mean to 3 standard deviations above the mean, and that means we need to be within 3 standard deviations. And the percentage for that was 99.7%. Now you're going to make me go double check. Yep. There was a moment when I thought maybe it's something else. 99.7%. We need to find 99.7% of 400. And it should be almost everybody. I don't know what it is though. (398.8) snack foods would have calorie counts between 55 and 145. That's what we would be expecting with a normal distribution. In reality, we're probably talking about 399 of the snack foods. I'm not sure we can have a decimal number of a snack food like 398.8. Here's another one to work on. Same kind of idea, but a different set of values. So we have prices of organic of organic bananas with a mean of 79 cents a pound and a standard deviation of 9 cents a pound. I set this one up the exact same way that I did the other one. I put the mean in the center and I add on standard deviations for 3 standard deviations above. I subtract off when I go to the left-hand side for 3 standard deviations below the mean. And then I usually come back through and check and make sure my additions are correct. I will let you double check on that for me. If we want our organic bananas to be priced within 2 standard deviations of the mean, what interval of prices are we talking about? Well, here's the mean here in the center at 79 cents. If we want to be within 2 standard deviations, it would be from 61 cents, because that's 2 below the mean, to 97 cents, because that's 2 above the mean. So 61 cents per pound and 97 cents per pound. Those would be the bumpers for the price range that we would be looking for. So that's what's going on here. And then we would expect a certain percentage of the bananas to be between 79 cents a pound and 88 cents per pound. I have an answer here, but let's go see how I got it. The question is asking about this chunk right here, from 79 cents to 88 cents. If I made the mirror image of that chunk over here on this side, then I would be working within 1 standard deviation of the mean, which would be 68%. So we know this whole entire chunk right here is supposed to be 68. Lost my percent sign. There it is. That entire chunk is supposed to be 68%, but we only want half of that chunk. We only want to go from the center out to one edge, and so we take half of 68% to get there. And that's where 34% comes in. Then we're going to change channels a little bit. You want to read this page about critiquing infographics, which is fancy talk for critiquing statistical displays or statistical statements or charts or graphs. There's some guidelines there. I give you some bad graphs and ask you to help out with what is wrong and how to fix it. The issue with this one is that the teams don't make 100% of something. Pie charts are for whole quantities split into chunks. This is 3 teams measuring their vaccine rate. It should be a bar chart of some form. And also the percentages don't add up to 100%. That's a flag that there's a problem. This one isn't a great plan. It took me a moment to find this one. When we look at axes on displays, they need to start at 0, or they need to give an indication that they've made a little jump if they don't start at 0. So axes need to be starting at 0, and they need to be evenly spaced out in terms of the units that we're using. This one doesn't start at 0. And what that does is it makes it look like this KFC bar stops here at half of the Taco Bell bar, for example. And that would be misleading, because 650 calories is not half of 720. It's a bit misleading. So to fix it, if they would fix their axis so that it starts at 0, that would be more accurate display of what's going on. And finally, you can make this one bigger with the expander. I'm not able to do it at this moment on the machine that I'm on, but you can make it bigger so that you can see what's going on down here with these dates. The dates don't go in chronological order. There's like a May 7th coming before April 26th. The information has been organized to make it look like the trend is going down over time, even though it wasn't. So this is very misleading and in fact dangerous in this case. And to fix this, we would need to rearrange the data. If you have questions about things that we have been working on, please let me know. Please reach out if anything is a concern for you in the stats unit. I'd be glad to get back with you.